My name is Masaki Hori of the Max Planck Institute for Quantum Optics and also the University of Tokyo of Germany and Japan. The universe has this duality between matter and antimatter. Duality means that for some reason, for every matter particle, there's always a corresponding antimatter particle. And we believe that the universe has a fundamental symmetry wherein the masses of these particle and antimatter particle are exactly the same. And this is a belief that we have of the standard model of particle physics. And here we have to verify whether this fundamental symmetry is correct or not. In fact, this symmetry is so fundamental in our understanding of nature that if it's broken, then we really have to rethink all our theories of particle physics. Here we measure the mass of the antiproton relative to the mass of the electron. This is called the antiproton to electron mass ratio. And what we do is we synthesize atoms that contain antimatter. This is atoms that are half matter and half antimatter. We produce them in this experimental target. We then shine laser beams on these atoms and measure their transition frequencies very precisely. What we do is we measure the color of these antimatter atoms very precisely. And then from this we can determine the mass of these antiprotons. Well, we can only say that our understanding of particle physics, which is based on our belief that the two particles should be the same, has been confirmed to 9 digits. But it does not exclude that maybe at the 10th digit or the 11th digit, as humans, technology advances, we can probe deeper and deeper and to higher and higher precision whether the two are the same or not. And of course, we've always liked to go to the highest possible precision because we don't know whether maybe at the next level of precision these things can be broken or not. In the next step, we believe we can measure the mass of the antiproton more precisely than for the proton. In that sense, we would know the properties of antiparticles, antimatter particles better than for normal particles. And this would allow us to probe deeper into how the universe is and how these matter and antimatter particles behave.
The ASACUSA experiment at CERN studies a special kind of half-matter, half-antimatter atom called antiprotonic helium, shown in this animation. Here, in black, is an antiproton orbiting around the nucleus of a helium atom. We fire 2 opposite laser beams at this atom, and this causes the antiproton to make a quantum jump, stripping away the electron shell and then pushing it into the helium nucleus, which results in annihilation of the atom.
So you wanna now I've said that my street system is in.
This is the peak corresponding to the signal from the antiprotonic helium atoms.